Okay, so I'm Helen Hayward and I'm a particle physicist. So how did I get here? Well, the short answer is curiosity, and I hated writing essays at school. That's the short answer. So when I was a child, I don't know if any of you had these, but I had one of those little the jewellery boxes where you open the lid and there's a fairy which goes around and the annoying music plays. And I did what any sensible little kid did. I went into my brother's room, stole his penknife and took it to pieces. I really wanted to know how did it work, and I liked the fact you could take it apart and you could see the drum with all the notches on and the comb. And that's essentially still what I'm doing. We want to understand exactly what are the fundamental, if you could really take that jewellery box and take it to pieces and then get to all the atoms and then start taking the atoms apart. What are the atoms made of? And then you have your protons, your neutrons and your electrons. Well, hang on a minute, I can take the proton apart, that's made of quarks and gluons, and really try to understand what exactly are the fundamental building blocks of nature. And we're doing quite well in the field, we're doing very well. So recently you've heard that we found the Higgs particle. So you think we were doing great. This is the last particle. We really understand everything that makes matter in the universe. Not quite. So if we take all the matter, everything that we know about the universe, and we sum it up in a simple pie chart, all the matter that we understand, that we are made of, the Earth is made of, my jewellery box is made of, the Lego blocks and the molecules are made of, is this little triangle up here. It's only 5%. We only understand 5% of the universe. Oh, that's a bit unsatisfactory. So this big wedge here, that is dark energy, and I don't have time to go into that, but it's effectively this mysterious force that's driving the expansion of the universe. What I will talk about is this dark matter, which is about 20-25% of the universe. So what is dark matter? Well, a little bit of history. So back in the 1970s, Vera Rubin was looking at galaxies. And if you look at galaxies, you can have, if you measure how much light, where the light is coming from, and you look at the visible disk, you can understand how the mass or the matter you think is distributed in the galaxy. Clearly, you've got sort of a bulge in the middle and it kind of peters out. And what you can also do, so everything you glow, you can kind of look at how bright it is and get to the matter. You can also have a look at how it rotates and the velocity of the galaxy as you go out in radius from the centre of the galaxy. And you can do this by using the Doppler shift. So this is, most of you are probably aware. So if the Doppler shift is exactly the same effect as when you have an ambulance. If an ambulance is coming towards you, the siren sounds that it's got a higher pitch than when the ambulance is going away. So it's the shift of the wavelength of the sound in the case of an ambulance. But it also works in light, so we have this Doppler shift. So we can measure the speed of the galaxy at different points from the centre of the galaxy. And we have a bit of a mystery. If we counted up all the visible light, what we expect the matter to be, we would expect to have this rotation curve. That's not what we see. We see this higher rotation curve. So the galaxies do not rotate as we would expect from the visible matter. So there must be other matter there, matter we can't see, matter that doesn't glow. Let's call it dark matter. And there's other evidence for it as well. We've got gravitational lensing. So if you've ever taken a photo or looked at a photo and there's a lens flare, well, gravitational lensing is pretty much exactly the same thing. So here we have a group of galaxies, and these blue lights here, they're not different galaxies, they're one galaxy. It's one galaxy right at the back, and the light from the galaxy is being distorted by the gravitational field of the dark matter, sort of somewhere in the middle here. So we know dark matter exists. Now, I'm not an astronomer. I've kind of misled you here for the last few minutes. I'm a particle physicist, so how can we understand dark matter coming from a particle physicist? Well, we have a tool, or rather an equation. So I think most people should know what this equation is. E equals mc squared. What it means is energy is mass, mass is energy. If we can create a high enough collision, we can create matter. We can create matter we know about, and we should be able to create dark matter, as long as we have enough energy. So how do we create high energy collisions? Well, there's this little place near Geneva called the Large Hadron Collider. and it's an accelerator 27 kilometres in circumference. And Geneva's down here somewhere. So the experiment I work on is called Atlas. And what the LHC does, it takes bunches of protons and accelerates in opposite directions and then collides them. And then we study what comes out of these collisions. Now, we can't choose what comes out of these collisions. We're just making collisions. E equals mc squared, it's spitting out mass. It's spitting out matter. So the Atlas detector, so here it is, or rather, here is a computer simulation of it. Now, if you see these little orange people there, that's the size of the scale. It's approximately 22 meters high, 44 meters in length. So it's a very large detector. Because we really want to be able to measure everything which comes out of this collision, all the particles, we really understand exactly what happened when these bunches of protons collided and created these events. And here is a photo just to prove that it really does exist and it's not just a piece of simulation. So this is the toroid, and you can see this corresponds to this toroid here. But that really is, unfortunately, because the cavern is built in a cavern, there isn't actually much space between the detector itself and the wall of the cavern, so it's really hard to get a photo with it all in. Okay, so we have the accelerator to accelerate the protons, and we have the detector. So this is what a reconstructed event looks like in the Atlas detector. So this view here, we're looking at sort of the head-on, so the protons are effectively coming inside and into and out of the screen. You're looking kind of head-on, and this is a side-on view. And what we see in this type of event is, we suddenly see, hang on, everything is coming out one side. That's a really funny collision. You can imagine colliding two billiard balls and they go in one direction. It's unnatural. It's indicative that there must be something invisible balancing the momentum, conservation of momentum. It's one of the fundamental rules of physics. There must be something invisible balancing this event, which doesn't interact in the detector. So whatever this is, it doesn't interact through electrostatic, electromagnetic forces. Therefore, it won't give off any photons. It could be dark matter. It might not be. It's something invisible. So these are the sort of events that we're trying to look at and trying to understand in order to see what dark matter could be. Now, coming back to where I got here, so this is just one of one example of what we can look at in particle physics. So how I got here, so I chose to do physics and maths for A-levels, and I went on to do a physics degree at Birmingham University. And at that point, I didn't know what I wanted to do. I was just choosing what interested me at the time, but I kept going to these more fundamental questions. What is matter? What is the most fundamental questions? And one of the particular reasons I really like dark matter is, this is also showing my age quite a bit. We're answering the same question, or trying to tackle exactly the same questions as astronomers are. We are looking in our microscopes at the smallest things, trying to understand what dark matter is. Astronomers are trying to understand the biggest particles, the biggest galaxies, the biggest objects in the universe. But we're trying to understand exactly the same thing. So it's another example of a mystery which is really combining different fields of science. And I think that's why it's of really particular interest to me. Thank you very much.